Imagine not being able to breathe. This has now become a concern for everyone during the COVID-19 pandemic, but has always been a reality for patients suffering from idiopathic pulmonary fibrosis, or IPF. In IPF, scar tissue accumulates in the lungs, progressively impairing oxygen diffusion and breathing. 40,000 new cases of IPF are diagnosed each year, the same number of patients who will die from breast cancer, and every IPF patient will sadly die within 3 to 5 years because no cure exists. Healthy lungs are able to readily expand and compress to exchange carbon dioxide with life-sustaining oxygen. This is because of the matrix. The matrix is a stretchy, elastic scaffold that holds cells to maintain the shape of our organs. With this elastic matrix, our lungs are able to readily change volume like a balloon. But what happens when the matrix in our lungs changes? In IPF, cells construct more matrix so that soft, pliable balloon is transformed into a tennis ball with stiff, restrictive material. This stiff matrix obstructs oxygen diffusion by replacing spacenet for air with regions of densely packed scar tissue. The cause of IPF is not known. The main question is, why do cells create unusual amounts of scar tissue in the lungs of IPF patients? Which is why I am designing a technique that will help define the cell types responsible for lung scarring and consequential stiffening in this disease. Previous research was limited by technology that only allowed for imaging of 4 markers to classify cell types. More cells can be classified using non-imaging techniques, but they turn normally solid tissue into a liquid solution that loses valuable information about how cells interact with scar tissue. I am now using a technique that preserves the shape of the tissue and increases images from 4 to 40 different cell markers. This enables me to investigate different cells in their normal environment with more detail than ever before. My results will identify what cell types directly interact with scar to promote disease, and if the types of cells occupying the lung changes in disease, such as what immune cells are recruited. I am then measuring the stiffness of the matrix, using an advanced method and designing a technique to overlap these measurements with the method that analyzes 40 cell markers. My research will allow for the first time in IPF the mapping of multiple cells unique to the disease state and not found in normal lung, with tissue stiffness, the defining characteristic of IPF. These results will help identify how disease cells contribute to scar generation and lung stiffening, revealing potential therapies for IPF patients. With these tools, we are one step closer to making that thoughtless breath you just took a reality for these patients. Thank you.